All right, for more still talking about aliens, one of the things we want to talk about is something called SETI. SETI, which is an acronym, stands for the Search for Extraterrestrial Intelligence. This came about or started way back in the early 1960s. We started wondering, because by that point we had radio telescopes, and we have radio telescopes that have been around for a while. And they started thinking that, we were broadcasting radio waves through satellites from one spot on the Earth to the other spot on the Earth. But we realized when you broadcast those signals, so here's our Earth here, what we do is if we want to say something live over here, like the Olympics are happening over here, you want to watch on your TV over here, the signal gets broadcast up to a satellite, then rebroadcast down to where your TV can pick it up. But the signal doesn't just stop at the satellite, the signal keeps expanding forever. So that since they started sending things by radio signals, which is back in the 30s and 40s, late 30s, one of the first signals sent was the Olympic Games in 1936, which were in Germany, in Berlin. But those signals are still traveling through space. So it's possible, if there was alien life out there, if they were within a distance to us and they turned a radio telescope like we have on the Earth, they could hear those broadcasts. They could hear the signals. They could get all our TV broadcasts, all our news broadcasts. They could learn all kinds of things about us just by listening to our signals. So that made them think, well, if they could listen to us, could we listen to them? Well, what limits the radio signals is the speed of light. So since these have been going now about 70, 80 years, any star within about 80 light years of us could pick up our radio and TV signals. Any stars further away than that, the radio signals have not got to them yet, and we would look just like a normal planet with no life on it. So they came up with this idea, well, let's search for extraterrestrial intelligence. Maybe there's other civilizations out there that are broadcasting their signals like we do, and if we just turn our radio telescopes, tune them to the right frequency, we could listen for those signals. And that came up with something called the Drake equation. The Drake equation was, well, is this really productive or is it not? So the question is, how many actual intelligences or civilizations with intelligent beings that we could communicate with actually exist in our Milky Way? And so they came up with an equation. The equation is the number n, which is the number we could communicate with, is equal to this kind of long equation. It's ns, fp, np, fb, fi, fc, fl. All right, so what does all this mean? Well, n, this is the number of civilizations that we could communicate with. We realize if that number is very small, good, that we could communicate with. Like only a handful, there's no way we could communicate in our Milky Way, which has several hundred billion stars. But if there's like millions of these, then there's a good chance there's one of them close enough. They have to be fairly close to us. All right, so what is NS? So the first term, so we're just going to go down each of them. NS is the number of stars in the Milky Way. Okay. FP is the fraction of those stars with planets. Because it's possible you can have stars and not have planets. Some binary systems could be disruptive enough that the planets just couldn't exist around them. NP is the number of planets around each star. And then FB, number of planets suitable for life. Because, you can have planets, but if you don't have life around it, not likely to communicate. Where FB is the fraction on which life is developed. Because you could have all the right conditions, but never have anything more than just rocks. Then you could have life, but Fi is the fraction that develops intelligent life. We're not going to be able to converse with microbes on a planet 50 light years away. So it has to have intelligent life, and it has to not only have intelligent life, but it has to be able to communicate. It's a fraction that can communicate. For example, we had life here, and we had human life for 2 million years before we finally got to radio telescopes, which allows us to communicate across space. Before that, we could not communicate with anybody else. Or you could imagine a civilization that has intelligent life but doesn't care, like the Amish or something like that, where they don't care about any technology. They want to stay in a very simple lifestyle. They might never develop radio technology or the ability to communicate across space. And then FL is the fraction of the star's lifetime that the civilization lasts. For example, if we learned how to communicate and then we blow ourselves up 100 years later, that means we only had 100 years in which to communicate. That's not a very long time. It's not likely we'll find another civilization. If we last for billions of years, like, 1/3 of the sun's lifetime, then we're around for a long time. It's much more likely to find another civilization over those billions of years that we could communicate with. So when we look at other intelligences, we have to think about, well, how long would they be around? The longer they're around, the more likely it is to communicate with them. All right, those are all the factors. Now we start putting in numbers. And we just start estimating. Now first, these are pretty accurate. Up here we have a pretty good idea of the number of stars in the Milky Way galaxy. The number of stars in the Milky Way galaxy is about 4 times 10 to the 11th, which is a lot of stars, okay? That's about 400 billion stars. So there's a lot of stars to choose from. Now the fraction of these stars with planets, with planets, and this is not just planets, this is planets that can sustain that have life, who knows? We're going to say about half. And that may be low. Meaning, right now it seems like when we're finding extrasolar planets that every star that can have planets has planets. It's pretty much a function of how they're formed that planets exist. But there are situations where the planets get disrupted, messed up, and they might have the right kind of planets in the right location for life to exist. And that comes down to the number of planets suitable for life. Well, for us, the number of planets is 0.1 that is suitable for life. Or about 1 out of our 8 planets is suitable for life, which is not really true because remember Mars is 2, so that could be as high as 0.2. Not a big deal. It's not going to make a big difference in the long run. Fraction at which life is developed. All right, this is where we start to split. We have the optimistic view and the pessimistic view. All right, everybody kind of agrees on those first numbers. In this one, the optimistic view says, you know what? If you have the right conditions, like the Urey-Miller experiment, you have the right conditions, life's going to form. You give it enough time, guaranteed life will form. That's a 1. That means that every single one, put the right conditions, right temperature, right chemicals, you're going to form life. The pessimistic one says, no, maybe that happens 1/10 of a time and we just happen to get lucky here. And then the question is, how many of those develop intelligent life? Okay? Well, we only have one example, that's us. We developed life, microbial life, and eventually became intelligent life. So optimists say, yeah, given sufficient time, there's always going to be some intelligent form of life that's going to develop on that planet. Pessimists say, no, that maybe happens 1 out of 10 as well. And then we have the fraction that can communicate with us. Well, that's, again, these are just guesses. They're saying, okay, well, we did, and given sufficient time, most cultures, but we can see that some aren't. So even the optimists say, well, maybe about half the cultures will develop a radio technology or some other means by which they can communicate across space. Pessimists say, well, maybe 1 out of 10. All right, this is where the numbers get very different. The fraction of the sun's lifetime, or the star's lifetime, that the civilization will last. Well, optimists feel that through technology, through cooperation, that humans are going to exist and we're going to exist for a long time. We're not going to kill ourselves off. And if you do that and you say then that the fraction of the sun's lifetime is going to be about 10 to the minus 4. Okay? Which means that we would be around for a good chunk of it, or about 1/1000th of the sun's 10 billion year lifetime. Several million years. Okay? Now, if you're a pessimist, you say, no, we're not going to last that long. We're probably going to kill ourselves off in a few thousand years. Then this becomes 10 to the minus 6, or 1/1,000,000th of the sun's lifetime. Okay, that's about 1,000 years is all. All right, now when you multiply all those together, what do you get? Well, for the optimistic view, you get 10 to the 6, or 1/1,000,000 stars. For the worst, or the optimistic one, you get 20. All right. So, if there are only 20 stars in the whole Milky Way,